Hi, my name is Katie Barbera. I'm a grade 9 student from Cathedral High School, and today I will be discussing a method of modeling hyperbolic geometry alongside an investigation towards its underlying principles in human anatomy, marine morphology, and the theory of special relativity. Hyperbolic geometry is an axiomatic system of constant negative Gaussian curvature that, although mathematically presented in 1856, has strongly been believed to be of impossible existence due to the human mind's difficulty in visualizing objects on a non-Euclidean scale. The most prominent difference between Euclidean and hyperbolic geometries is with regards to the parallel postulate contradiction. This can be visualized through the utilization of two lines and a dot. In Euclidean terms, it is believed that, given a line and a point not located on that line, there can be only one other line that can pass through the dot without ever intersecting the original line. Any other line would have a different slope, and thereby cross the first line at some point. In hyperbolic geometry, it is observed that, through a point not present on a line, there is a minimum of two lines parallel to that given line. As displayed in hyperbolic geometry, two lines parallel to one another are found to converge in one direction and diverge in the other. In comparison with reference to Euclidean geometry, parallel lines measure equidistant at all points. Similarly, although following common theorems, there are several other discrepancies found within geometric properties, such as the sum of angles within a triangle or the similarity of polygons with differing areas. It was not until 1997 when the first functioning physical model of hyperbolic surfaces was created, through means of crochet. By using the method of crochet, this study aims to model and analyze the physical characteristics of hyperbolic space, to contribute towards a deeper understanding of the Earth's geometric plane. The hyperbolic surface being modeled is a replica of coral reefs, abundantly found within oceans around the world. As this is an exploratory research study, it is difficult to provide any precise hypothesis. However, based on previous knowledge of geometric properties and extensive reading on hyperbolic nature, certain projections may be developed. In order to model this form of structure using crochet, a pattern in which the number of stitch increases are exponentially augmented per row will be implemented. It is hypothesized that, beginning with a flat surface of circulating knots, the increasing number of increments within a restricted surface volume will cause the walls of the crocheted coral to fold into each other, thereby creating the negative curvature displayed in nature. The modeling of hyperbolic space through the means of crochet was implemented using a medium-weight 100% acrylic yarn and a 4mm hook. The magic ring method was used to begin the structure, as its tightly bound center provides the ideal base when crocheting in rounds. The starting row encompassed 6 stitches, and the tail of the ring was pulled tightly to largely eliminate the presence of a hole. Following the ring of 6 single crochet, each round grew through the pattern of 1 single crochet followed by 1 increase, thus increasing exponentially at a 3:2 ratio. By rapidly increasing the amount of yarn woven into a restricted area, the figure quickly began to twist itself, forming that negative curvature characteristic of hyperbolic geometry. This model was halted following the completion of 13 rounds. However, through the utilization of the aforementioned pattern, an infinite number of rows could continue to be added, with each round of stitches corresponding to an increased presence and complexity of curvature. To further examine how rate of increase influences the evolution of curvature in hyperbolic space, 2 additional models were crocheted. The second structure observed a sequence of 3 single crochets, followed by 1 increase. Through repetition, the material began to curve, however at a much slower rate and intensity than the first model. The last structure followed a design in which each stitch contained an increase. The results from this trial exhibited very rapid curvature, thereby consuming large amounts of yarn relative to its small volume. Upon completion of the models, the symmetry and curvature of the hyperbolic plane was examined to prove that these structures accurately modeled the hyperbolic geometry. To ensure that the model was of negative curvature, the displayed equation was solved, where C represents the intrinsic circumference with intrinsic radius r on a hyperbolic plane of radius r. The circumference of each model was calculated to be 70.6 centimeters, 44.9 centimeters, and 56.7 centimeters, respectively. Since the resultant value is greater than 2 pi r, the circumference of a Euclidean circle, the structure is, by definition, of negative curvature. Finally, the crocheted model was used as a visual to better demonstrate the abstract properties described by hyperbolic geometry. Divergently parallel lines in which two segments diverge from each other in both directions was vividly displayed across the structure, spanning perpendicular to the crocheted rows. Similarly, asymptotically parallel lines, those which converge in one direction and diverge in the other, were visible. Lines perpendicular to the crocheted rows were determined to be straight, as the model was folded without stretching. These exciting observations supported the disapproval of Euclid's fifth postulate in displaying that there is not one, but instead infinite number of parallel lines that may touch an external point without ever intersecting each other. Hyperbolic geometry's interpretation of triangle measurements was likewise examined. 3 points on the fabric were chosen, then connected by straight lines, once again determined by folding the figure without stretching the material. The negative curvature of this plane forms a triangle, whose interior angle sum is less than 180 degrees, a relationship that once again contradicts the commonly used Euclidean depiction. Another interesting concept is highlighted by this demonstration relates to the inexistence of similar triangles in hyperbolic geometry. As a result of three-dimensional interpretations, all triangles with equal angle measurements are considered congruent, as the side lengths are dependent on how close the object is from the edge, thereby allowing for every triangle to be rescaled without distortion. The results of this study show the exponential growth, an infinite space that hyperbolically geometric structures are characteristically capable of occupying. Maximizing surface area within a restricted volume has critical implications toward various aspects of nature, ranging from sponges to the complex modeling of the human brain. By developing a greater understanding of hyperbolic space, great advancements may be made within a variety of scientific fields, such as computer tomography imaging and reconstructive surgery, or a scientific understanding of the shape of our universe. As examined throughout the study, from a double helix of DNA to the shape of the universe, hyperbolic geometry presents infinite applications towards all aspects of existence. Within this project, a coral reef resemblant structure was modeled through the use of crochet to provide a physical representation of hyperbolic space. Various analyses examined the postulates of hyperbolic geometry and demonstrated the unique properties that contradict the more intuitive Euclidean interpretation of space. 3 crocheting models were created, with unique rates of increase, to investigate the related influence towards curvature. Further knowledge was gathered regarding the increased circumference and surface area of the intrinsically measured circles on the hyperbolic plane and Euclidean plane was compared, with appreciably greater values resulting from the hyperbolic surfaces. This knowledge relates to various aspects of nature in presenting possibilities of maximized surface area. Likewise, hyperbolically trigonometric properties were explored, thereby touching upon the theory behind special relativity and its computational simplification through the use of hyperbolic functions. Future studies should continue to investigate new models of hyperbolic space, including the impact that hook-sized yarn material has on curvature. Through the development of a concrete method for fabricating hyperbolic space, many challenges requiring vast surface area within a minute volume, such as the creation of artificial lungs, will be progressed.